Welcome to The Explainer. Okay, today we're diving into an epic and honestly completely unlikely marriage between two wildly different worlds. Picture, on one hand, the blazing, chaotic, swirling solar plasma of a massive star, right? It's violent, it's unpredictable, it's blindingly bright. Now contrast that with the glowing, pixelated screen of a chunky 8-bit arcade cabinet sitting in a 1980s pizza parlor. I know, it sounds like pure science fiction, but this bizarre crossover is actually solving one of the most frustrating computational bottlenecks in modern astrophysics right now. Okay, let's dive into this. What could 1980s computer graphics possibly have in common with the sun? You might think absolutely nothing, right? Well, for decades, astrophysicists have been banging their heads against a wall trying to simulate exactly how light moves through stars. It's an absolute mathematical headache that has severely bottlenecked our understanding of the universe. But it turns out a retro rendering trick, something originally designed decades ago to stop early video games from crashing on severely limited hardware, is the exact key researchers are now using to decode stellar physics. By borrowing this clever hack from early computer science, they are finally bypassing a massive roadblock.
Section 1. The Stellar Math Problem, Navigating Non-LTE Plasma Challenges.
To really appreciate why this is such a monumental breakthrough, we first need to grasp the sheer mind-bending scale of the challenge. Astrophysicists study something called non-LTE stellar plasma. That stands for non-local thermodynamic equilibrium. Basically, in these extreme environments, you can't just measure the local temperature to understand the energy. The atomic energy levels in the plasma are completely dictated by the surrounding radiation field, which means you have to calculate the light interacting from literally every possible direction. And that brings us to this staggering number, 7. Can you imagine trying to calculate physics across not 3, not 4, but 7 dimensions at once? When simulating this radiation field, scientists aren't just dealing with a standard 3D grid. They're tracking 3 dimensions of space, 1 of time, 2 for the exact direction of the light rays, and 1 for the wavelength. To figure out the physics of the star, they have to calculate this dizzying 7-dimensional puzzle over and over and over again for every single microscopic point in the volume. For like the last 30 years, the astrophysics community essentially relied on 2 main methods to solve all this intense math: long characteristics and short characteristics. Think of long characteristics like a highly calibrated sniper rifle. It traces light rays all the way to the boundary of the grid. It's incredibly precise, and it's what scientists call embarrassingly parallel, meaning supercomputers can easily divide up the work. But it is astronomically heavy and agonizingly slow to compute. Short characteristics, on the other hand, is a bit more like a shotgun. It's much faster because it only traces a ray a short distance and then just kind of estimates or interpolates the rest. The problem? It's way too messy and diffusive. It totally blurs the physical accuracy of the simulation. So researchers were basically trapped in this frustrating compromise. You either get painfully slow perfection or fast but blurry estimations.
Section 2. The Traversal Problem, Why Simple Averaging Fails.
Now you might be thinking, hey, if the math is too heavy, why can't we just group a bunch of nearby grid spaces together and average out their properties to save time? Well, that introduces a core roadblock known as the traversal problem, and this brilliantly illustrates exactly why. Look closely at this setup. We have 4 blocks, or voxels. The top 2, A and B, represent one set of physics, let's say a clear window. The bottom 2, C and D, represent thicker, denser physics, like a heavy fog. Now look at ray alpha, shooting straight down, and ray beta, shooting straight up. They travel through the exact same physical space, just in opposite directions. But because these blocks have what's called non-trivial optical thickness, light is absorbed and emitted completely differently depending on which block it hits first. So hitting the fog before the window produces a vastly different result than hitting the window before the fog. The order of traversal literally changes the physics. Let's look at the actual numbers here to see just how disastrous this is for anyone trying to simulate a star. If you calculate the true intensity for ray alpha passing through those specific blocks, you get 0.78. But for ray beta traveling the opposite way, the true intensity is 2.00. Now look at that average column right in the middle. This should be ringing massive alarm bells. If we had just taken a flat, simple average of the physics in those 4 blocks just to save some computing time, both rays would spit out an intensity of 1.29. Think about how wildly inaccurate that is. I mean, 1.29 is incredibly far off from 2.65 for ray gamma or 0.25 for ray delta. You are fundamentally destroying the science.
This completely proves that you just cannot blur chaotic stellar plasma into a flat average without generating catastrophically bad data.
Section 3. Borrowing from video games. A retro rendering trick. Faced with this impossible physics wall, researchers completely shifted gears. They actually looked outside of their own field and pivoted straight to computer graphics. Which makes sense, right? Video game developers have been fighting the exact same battle of efficiently calculating light rays in complex 3D textures since the dawn of the medium. And the groundbreaking answer they found came from a specific technique invented way back in 1983 called Mipmapping. The word mip comes from the Latin multum in parvo, which basically means many in small. Back in the 80s and 90s, gaming consoles had severely limited memory. If a game tried to render a high-resolution brick wall far away in the background, the screen would produce aliasing, those weird flickering, glitchy patterns. To fix this, game engines were programmed to intelligently blur and compress textures that were further away from the player. It saved precious memory, smoothed out the final image, and most importantly, kept the game from crashing. Now, what's really interesting about this is seeing the comparisons side by side. On the left, you've got the absolute highest resolution simulation of chaotic solar plasma. This is MIP0. But look over to the right at MIP4. This is a highly compressed, massively averaged, blocky version of that exact same space. It is absolutely wild to think about viewing the complex astrophysics of a star through the lens of a blocky retro video game texture, but that is exactly what's happening here. The computer graphics trick tells us we can mathematically compress the data by halving the resolution layer by layer, just like a video game loading distant scenery. But because of the traversal problem we just talked about, we know we can't just slap this blocky version everywhere, or we'll completely ruin the astrophysics calculations. Section 4. Variance-limited mipmapping, smart data compression. So to solve this, the researchers developed a brilliant hybrid called variance-limited mipmapping. Basically, the algorithm has to be incredibly smart. It needs to know exactly when it is mathematically safe to use that blocky, efficient 8-bit version, and when it desperately needs to preserve the gorgeous but computationally expensive high-resolution data. The secret sauce driving this decision is a metric called the index of dispersion. It works like this. The algorithm scans the physics of the star. If it sees a smooth, quiet area of space where the temperature and density are barely changing, the index of dispersion is low. The algorithm flags it and says, great, use the blocky, super fast compression here. But if it detects a chaotic shock jump or a massive spike in radiation, the variance is high, and it immediately forces the grid to stay at maximum resolution. And the result of this clever sorting is staggering. By applying this video game logic, researchers found that less than 12% of the voxels in their simulation actually needed to be calculated at maximum resolution. Less than 12%. That means an unbelievable 88% of the simulation could be safely compressed without losing a shred of scientific integrity. And here is the visual proof of this highly intelligent algorithm in action. Take a moment to look at these heat maps, mapping that index of dispersion across different levels of compression. Notice those neon-bright, highly illuminated areas tracing the jagged edges? That is the algorithm actively hunting down the complex, turbulent shockwaves of the plasma that desperately need high-resolution detail. It's literally isolating the chaos. Now look at the deep, dark areas, the calm voids in between. That is the algorithm efficiently ignoring the empty or uniform space. In those dark regions, it's safely swapping in the blurred-out video game-style mipmaps, saving massive amounts of computing power without hurting the final scientific result. Section 5. Accelerating ray tracing, VDB and HDDI traversal. So the crucial point is, now that we have this incredibly smart hybrid resolution grid, how do we actually shoot our digital light rays through it? Well, the researchers adopted a super powerful data structure famously used in Hollywood visual effects called VDB, which surprisingly isn't actually an acronym, and they paired it with a traversal technique called HDDA. This combination completely transforms the journey of a simulated light ray into a really elegant three-step process. First, as the ray moves, it actively checks the spatial grid's index of dispersion. Think of the ray like a sports car, right? Step 2, when it enters those huge, blocky, mip-mapped regions of quiet space, it's like hitting a long, empty, perfectly paved highway. The ray hits the gas and practically fast-forwards, skipping over massive chunks of the domain in single, highly efficient calculations. But step 3,
The second the ray hits a chaotic, high-variance shockwave, it's like turning onto a treacherous, bumpy dirt road. It slams on the brakes and immediately drops down into the micro-level grid to navigate the complex physics point by point.
And here, we finally arrive at the massive payoff of this entirely unlikely crossover between 1980s texture rendering and 21st century astrophysics. Remember that frustrating 30-year struggle we talked about earlier? That endless, awful compromise between the agonizingly slow sniper rifle and the blurry, inaccurate shotgun? Well, by implementing this variance-limited mipmapping into their new code, which is called DexRT, these researchers absolutely shattered that compromise. They achieved a staggering 10-time speed boost in calculating the stellar radiation field. A 10x acceleration for a computational bottleneck of this magnitude is just monumental, and the cost to the actual science? Almost non-existent. They maintained less than a 0.5% error in the 99.9th percentile of their atomic population calculations. So they effectively unlocked the extreme, flawless accuracy of the old, long characteristics method, but pushed it to the blinding, hyper-efficient speed of a modern video game engine.
Section 6, The Future of Simulations, Interdisciplinary Answers. Honestly, this entire journey highlights a profoundly powerful lesson about big data and modern science. When an entire discipline is stuck on a crippling math problem for 30 years, the answer rarely comes from simply doing the exact same thing, just slightly harder. Looking outside your own specific field is the ultimate game changer. These researchers realized that simulating the 7-dimensional radiation field of a star is, at its core, really just a hyper-complex version of rendering lighting on a 3D video game texture. Interdisciplinary thinking is actively breaking down the walls of what we thought was computationally impossible, which leaves us with a fascinating, lingering thought to take away today. If a simple graphics hack from a 1983 vintage video game can efficiently decode the overwhelmingly complex radiation of the stars, what other everyday, overlooked technologies are currently holding the keys to unlocking the rest of the universe? Keep your eyes open. The next great scientific breakthrough might just come from your living room.